Welcome to Off Hours, a conversation between Jon Edwards and Chris Manning.
One of the recurring topics that we've discussed and sort of talked a little bit around, but not really gone into any detail. We've talked about free sprung balances a little bit, as well as things like tourbillons and other methods of regulating time in modern watches. And I know I've had a few questions come up with people who've listened to previous episodes asking about it. I thought it might be a good time to talk a little bit about measuring time and how we go about measuring time in modern watches, as well as a little bit of history as to how mankind has attempted to measure time in the past.
I guess if we drop back to square one, the whole purpose of measuring time, the whole reason we began measuring time was just a reflection of what's going on up overhead with the passage of the sun and the stars. If I remember correctly, you have seen the largest sundial in the world in some of your travels. You want to chat a little bit about that, just to lay some initial groundwork for why on earth we try to measure time at all?
Anybody who pays attention to what's going on around them in the world, it's easy to see the differences in the length of days, where the sun is setting and rising as the year changes, and of course as it gets warmer and colder with the season. So it's natural that humans will have tried to keep track of that. And of course, it's important when you're becoming an agrarian society. You need to know when to plant your crops and when to take them out of the field. And I think the earliest attempts to measure time accurately were using a gnomon, which is effectively a stick in the ground. It could be even something as simple as a tree, and you can mark off the divisions of time on the ground where the shadow of the gnomon lies, thanks to the sun. And eventually mankind creates a calibrated gnomon attached to a sundial. I think I've read that the earliest ones were sort of Greek and Roman. So the people have been using sundials for quite some time, and they still remain popular today. In the 18th century, the Mughal Emperor Muhammad Shah, I believe is how it's pronounced, he created this massive collection of astronomical measuring instruments in Jaipur in India. The most impressive of them is the Samrat Yantra, and that's the this massive sundial that you alluded to that I've seen. So when we were there in 2012, we had a chance to wander through Jaipur for a few days. It's a beautiful city. We spent the afternoon walking through this incredible sort of park that was created with all these massive instruments for measuring things like the motion of stars and things like that. But this sundial is pretty impressive. I think it's about 27 meters tall, and it's large enough that you can watch the progress of the sun moving across the dial. So it moves around 1 millimeter per second. Over the course of a minute, you can watch the sun move by 6 centimeters, which is rather impressive. And again, you can actually sit there and watch the sun moving across this sundial. Something like that's incredibly accurate. Obviously, some of these smaller ones are not going to be nearly as accurate as that. And the larger they are, the more accurate a sundial is going to be.
Yeah, one of my favorite sundials is nowhere near that large, and you'd certainly be hard pressed to actually watch the motion of the shadow, or in this case, it's actually the beam of light from the sun traversing across the dial. You'd have to stand there for quite some time. But the particular sundial I'm thinking about is the dolphin dial at the base of the hill that the Royal Greenwich Museum sits atop. And it's just this really beautifully carved and intricate statue of two dolphins sort of jumping or arched up out of a wave, and where their tails come and almost meet at the apex of their jump, there's an area where the sun can beam down through onto a concave surface that that line of light travels across over the course of the day. to let you know what time it is. But sundials are sort of a fascinating subject all their own, and certainly the most accurate representation of how much sunlight is left in the day, or how the time is passing according to the sun, which is ultimately what all of our time measurement, mechanically speaking, became to be derived from. And now we've gone on to measure things with far more accuracy with atomic clocks, and now we're moving on to phasars and quasars and things like that. Now, one of the tricky things about measuring time with the sun, though, is that depending on where you are on the Earth, the amount of sunlight that you get through the course of a day is going to vary. So your hours are going to shrink or expand, so to speak, which Chris alluded to a couple episodes back with the Wadokai timepieces that were made by Masahiro Kikuno.
But of course, one of the big problems with using a sundial to measure time is that you need the sun in the sky to be able to actually measure time. And depending on where you are in the world, you may not get very much sunlight during the day. The farther north, of course, you go, the less sunlight you have during the day. And then you also run into problems of living in a country where it's overcast and you may not see the sun for many days. And so a sundial isn't necessarily the most convenient thing when it comes to measuring time.
Yeah, I was quite fortunate that the dolphin dial was actually displaying the time the day I was there. Because when you're living in Greenwich or London, the forecast is, well, the weather report is always that it's either rained, raining, or about to rain. So very rarely do you actually get to see the sun throughout the year there. So
London's not that bad, John. Stop saying that it's that bad. London is not that bad.
Well, I'm sure you're enjoying yourself. I certainly enjoyed my time in London when I got to frequent it on the weekends, and I was very fortunate to get quite a few sunny breaks. But it was often quite overcast, and perhaps that's the reason that Greenwich came to be the center of measuring time, and why London and England in general became such a strong force in the history of measuring time mechanically.
If you're listening while this podcast has been published, then I'm currently in London, but we're recording this the week ahead of time. So I unfortunately won't have time to go to Greenwich while I'm there this time. But when I'm back in August and September, I will be making a trip out to Greenwich, and then I will be sure to check out this sundial. But of course, as we say, sundials are only really useful when you've got sun. So we've been trying to create ways of measuring time mechanically for quite a while. The first significant attempts at measuring time with any degree of accuracy start coming in the 14th century. And we see virgin follet clocks being created, first as tower clocks. So you've got a large tower clock in the center of a town. And then eventually we, towards the middle of the 14th century, we start seeing small chamber clocks being made with a virgin follet escapement. And while they are certainly an improvement because you don't need the sun to be shining, and you can tell the time after dark, and you can set up alarm clocks and things like that, or you can have this large clock in the central square that you can reference. They're still not particularly accurate. I've been looking at making a replica of a 14th century clock, and an acquaintance of mine made one a number of years ago. I think he was keeping it accurate to within around 20 minutes a week, which isn't particularly accurate when it comes to a timepiece. Now, fortunately, towards the middle of the 17th century, Christian Huygens figures out the relationship of the length of a pendulum to a period of its swing, and figures out that it can be used to accurately regulate a mechanical timepiece. And for several hundred years, the pendulum becomes the most accurate way to measure time and create an accurate timepiece. He also is the one who invents the hairspring. I wasn't aware that it had been invented so early on in timekeeping.
Well, Robert Hooke might throw him a right hook on that one.
Oh yeah, you think so?
There's some contestation there, but documented it's Huygens.
Yeah, you're still talking the sort of 1675, somewhere around there. So that's quite early on in terms of timekeeping, mechanical timekeeping, and regardless of who it is, it's still pretty early on. I guess we want to talk a little bit about what's going on in a modern mechanical watch. I mean, obviously these older watches, they don't really relate to what we're doing today. Been a number of significant changes in the way that we tell time since the 17th century. Particularly, we're carrying these things around on our wrists instead of having a large clock in a tower or on a table even. So, I guess in a modern watch, what is actually regulating that watch so that it divides up the day into an equal number of seconds?
Well, for obvious reasons, you can't use a pendulum because a pendulum depends on gravity. In a perfect mathematical model, it would be gravity sustaining it. If you didn't have any sort of friction or air resistance, that pendulum would just keep swinging back and forth. But in reality, you need some outside force to continue that motion of the pendulum. But it's ultimately the force of gravity that is causing the motion. But because a timepiece that is worn on the body is not kept in a fixed position, gravity isn't able to be that sustaining force. So what you have instead is a spring, and both a spring-driven mass and a pendulum are harmonic oscillators. In theory, without any sort of outside disturbances, once set in motion, they would continue in that motion at a very precise interval of time that would be constant and would just continue on in that way. So in a modern mechanical watch, what you essentially have acting as your oscillator, which is what we'll refer to this as, is a wheel, which is a balance wheel, and where the mass is distributed largely around the perimeter of the wheel. And then you have a spring that is a hairspring that if you were to pull this wheel and turn it and then let it go, the wheel would push on the spring to a certain point, and then the spring would push back on the wheel, and that cycle would just happen back and forth and back and forth. And the hairspring is curled up in a form similar to, say, a snail's shell, so arced in on itself. And that would be a modern hairspring, a very simple flat hairspring.
If somebody's looking at the back of a watch, let's say that has a crystal on it to see into the movement, the balance and the hairspring you're talking about are the little wheel that's vibrating back and forth, and sort of the coiled spring that's underneath it. That's what you're talking about.
That's correct. And it would be, if you happen to have a skeletonized piece, it's the spring that's moving very rapidly back and forth. It looks like almost like it's breathing. Whereas if you have a barrel that happens to be skeletonized, you would also see another coiled spring, but that's the main spring, the power source of the watch.
It's important to mention that the hairspring that's there is really not the power source of the watch. The power source is going to be that main spring that's coiled up and providing sort of constant force to the whole mechanism. And the hairspring and balance are what are generating the regular period that you're then dividing up.
Mm-hmm. Yeah, the role of the hairspring is to push the balance wheel back from where it came from, or to pull it back once it crosses that point of rest. So depending on which direction the balance wheel is moving in, the hairspring will either be contracting or expanding. So it'll expand to its outermost point for the amount of energy that the balance wheel is vibrating with, and then it will contract in on its innermost point based on the amount of energy, and then it will restore that energy back, and just goes back and forth and back and forth. For every action, there is an equal and opposite reaction.
Really, it is acting like a pendulum. It's just, instead of it sweeping in an arc, it's spinning around that center point.
Mm-hmm. And rather than gravity being helpful, in this case, gravity actually tends to be an enemy of precision.
Sure. And that's where we start getting into complications like the tourbillon and the multi-axis tourbillons that we've mentioned in the past.
Mm-hmm.
So we're taking this balance, which is vibrating back and forth, and the hairspring that's assisting it. How is that motion being turned into something that can regulate the time in the timepiece? Because that mainspring, presumably, that's driving it, wants to just release and unwind completely as fast as possible. So how is that balance wheel, how is it being controlled and harnessed to regulate the time in the watch?
So this is where the escapement comes into play. So the escapement's an interesting mechanical device in that it is both acting as a means of transmission of energy to the oscillator, but it is also performing the division of time. So taking those regular motion of the oscillator and transferring that motion back into the gear train so that the gear train will be unwinding at a regular rate and allowing the device to display the time. So the tick tock that you hear in, say, a mechanical clock or a mechanical watch, that tick tock tick in a grandfather clock, say, that is the escapement moving back and forth. And on each tick and each tock, it's transferring some energy to the pendulum, or in the case of a wristwatch, it's transferring the energy to the balance wheel. And if you really zero in on the tick-tock sound, you can actually break it down even further, and you actually get a sound that's caused by the pendulum or the balance wheel unlocking the escapement, where it's first coming back into contact with it. So that's the point at which the measurement of time, which the oscillator is responsible for, so the pendulum and the balance wheel are what are breaking time down into very small slices. And then from there, there'll be a follow-up sound that's usually louder, where the escapement is then transferring the energy to the pendulum or the balance wheel. So the two work back and forth harmoniously.
Okay, so that transfer of energy back is what's allowing us to operate in a non-idealized world where we actually have things like friction and air resistance and things like that are slowing down either the balance or the pendulum.
That's right.
Now, when we're talking about hairsprings, one of the things that you'll see when you're reading about the statistics of a particular watch is the frequency that the watch is oscillating at, or the frequency that hairspring is vibrating at. Talk a little bit about why there's differences in those oscillations. Like what's going on there? Why is one oscillating at a different rate than another watch?
Well, there are two different ways we could approach that. So there are the physical reasons why that's actually occurring, or there are the ideological reasons why one watch will run at a faster pace than, say, another. As we've talked about in other episodes, everything is a trade-off. So ideologically speaking, a faster rate will be less susceptible to outside interference, but have a shorter power reserve and be more likely to wear out quickly as far as the actual mechanics of the piece are concerned. A slower rate is more susceptible to outside disturbances. So if you say receive a hard knock in between a tick and a tock, it can throw things off. But you get a longer power reserve, and you also end up with a watch that's going to last longer than one that's running, say, twice as fast. So a fairly typical rate in years of old would have been 18,000 beats per hour. And ship's chronometers will be even slower than that. The happy middle ground that the industry seems to have settled on is about 28,800 beats per hour. But there are some watches where, that will change. You end up with 21,600 beats per hour, or say in the case of the Longines annual calendar we were talking about in the last two episodes, that base caliber typically runs at 28,800 beats per hour, and you get a power reserve of about 2 days. But in the Longines annual calendar, what they've done is dial it down so that it's running at 25,200 beats per hour, and that gives you a longer power reserve. They've also done some other things to increase that power reserve, but a big part of it is decreasing that rate from 28,800 beats per hour down to 25.2. So you get about 64 hours, if I'm remembering correctly, out of that new caliber from Longines.
That's a convenient way of getting a little bit more power reserve without necessarily putting either a second mainspring or a larger mainspring in, because obviously in a wristwatch you are limited in the amount of space that you've got in there.
Mm-hmm. Now, to the best of my knowledge, the Longines does have a slightly longer mainspring than you would typically find in the base caliber, which is an ETA 2892. Now, as for the the physical reasons that this occurs. Basically, what you're looking at is a shorter hairspring will beat faster, and a longer hairspring will beat slower, and a heavier balance wheel will beat slower, and a lighter balance wheel will beat faster. And same goes for the diameter of the balance wheel. So if you think of a figure skater spinning around in circles, when their arms are in tight, they're going to spin very fast, and if their arms are out wide, they're going to be spinning slower. So that's why you'll see them spinning faster and faster as they draw their arms in.
Sure. So same thing's going to happen here with the balance.
Mm-hmm.
So earlier you mentioned gravity being a problem in watches, where it's an advantage in a pendulum clock, where you're taking advantage of the gravity to drive the pendulum. How is gravity causing problems to the balance and the hairspring?
It's good that you mentioned both the balance and the hairspring, because gravity affects them both, and both in different ways, and both impact the regularity at which the balance wheel is going to oscillate back and forth. For the balance wheel itself, really it just comes down to the balance. It's called a balance wheel for a reason. So you want this wheel ideally to be perfectly balanced around its axis, so there isn't a heavy spot on one side or the other. Now, this is much easier said than done. So a very finely regulated timepiece will have a balance wheel that is nearly perfectly poised. That is to say, if you were to put it down on a perfectly flat, perfectly smooth surface, just resting on its pivots, and puff some air on it, it would just come to a rolling stop, just very gently. Whereas if there's any sort of heavy spot on it at all, what you would find there'd be just a little bit of back and forth motion when it comes to a rest. Or if there's a really heavy spot, you would actually see the balance wheel roll back on itself a number of times before coming to rest. It would just sort of oscillate back and forth until coming to rest, where with the heavy point being closest to the ground. Now, with the hairspring, what you get is, depending on the position that the watch is in, the hairspring is always going to be pulled down more towards gravity. So it's working around the axis of the balance wheel, and gravity is going to be pulling down on this very delicate spring. Now, where this can really come to be a problem is when you just have a very simple flat hairspring. If you watch the action of this hairspring, you'll find it will jut out really far on one side when it's in expanding, and it'll pull in really tight and be tighter on one side than the other again when it's contracting. And what you have then is a hairspring that's not breathing concentrically around the axis of motion. So when the watch is in a position where it's expanding most on one side, and that side happens to be facing down towards gravity, it's going to pull even more on that side of the spring and exaggerate that effect, and in turn impact the rate. And same goes for vice versa. When that area of the spring that's really trying to expand outwards, when it's acting against gravity, gravity's trying to pull it back that whole time, and the amount of expansion that you're getting out of the hairspring isn't going to equal the amount of expansion that you're getting 180 degrees from that position. So then you get a variation in how fast the balance wheel is moving back and forth between the two. So ideally what you want is a hairspring that is expanding in and out concentrically around the center of rotation of the balance wheel. And the gentleman who first cracked this problem was, of course, Abraham Louis Breguet, with the Breguet balance spring, or Breguet hairspring, where you actually take the outermost coil of that spring and you bend it up over the other coils of the spring with a very specific geometry, of which there are numerous perfect mathematical representations of different ways to form this overcoil. This is what it's referred to as, because it's going up and coiling over the rest of the coils. And this allows the hairspring to breathe in and out so that it is essentially perfectly concentric around the axis of rotation. And this helps to eliminate any errors due to gravity acting on the hairspring. So the way that it's acting on the hairspring is equal no matter what position that hairspring is in.
Now, when you get to say that you're getting deviations in time and regulation, Are you talking about it just being slower or faster through the day? Or are you talking about, let's say, the length of a second changes depending on the position that it's in throughout the day? Like, are you getting, is this sort of averaging out over the whole day, or are you talking about getting specific increases and decreases at different times or different positions?
So it'd be specific increases and decreases based on the position that the watch is in. So there are positions that we tend to wear our watches in most throughout the day, but not all of us is absolutely consistent in that. So ideally, you want a watch that's going to perform the same in all positions. So it will literally change the length of a second as measured by the watch, say with the crown of the watch pointing down or the crown of the watch pointing up.
Okay, so I guess the ideal setup would be that you're, regardless of which position it's in, you're not going to be gaining or losing time regardless of that setup.
That would be the ideal, but realistically, what you're looking at is having a hairspring work in such a way that no matter the position that it's in, there isn't going to be a variance between the positions. So you might still be, say, gaining, you might still be losing, because there are numerous other factors and variables at play, but you want to minimize any errors that are introduced by the balance spring. So the overcoil is one way, and now with newer materials like silicon, we're looking at flat balance springs that can achieve the same effect just through the geometry of the spring itself by having thicker and thinner portions of the hairspring.
Now, in the case of a pendulum, the length of that pendulum is what dictates the period of its motion. Creating a pendulum rod that's not affected by temperature so that it doesn't contract or expand as the temperature changes is a significant part of building an accurate pendulum clock. Is there a similar problem with a balance? Because as the temperature is going to change, especially as you're wearing it, I imagine that balance is going to change in diameter. Is that going to affect the performance and the accuracy of it?
Yes, absolutely. Thankfully, Charles Guillaume cracked this problem quite well by inventing alloys of metal that are essentially impervious to expansion and contraction, or basically being affected by changes in temperature for the reasonable range that you can expect a watch to be running in.
Okay.
So he invented Invar and Alinvar, which basically stand for invariable, invariable, and for the Alinvar, it's that elastique invariable. So invariably, the elasticity of the alloy is invariable. And Niverox is owned by the Swatch Group, and is essentially using an alloy based on an Alinvar for all of its hairsprings. And they supply the vast majority of the Swiss watch industry with hairsprings. Then you've got Rolex, which has their own unique flavor in Paragrom.
So that's for the hairspring. Is something similar being, like, are they using these metals for the balance as well, or is there a different process for taking care of the balance?
So those specific alloys are referring to the balance spring. And then for the balance wheels, there are alloys as well that basically resistant to thermal expansion within a reasonable range of temperature. Most balance wheels today are made from a form of beryllium copper, but you also get balance wheels made of all sorts of other materials as well that remain relatively stable. But prior to the advent of these magical alloys that resist changes in their dimensions when subjected to changes in temperature, the way that they tackled this problem was with a split bimetallic balance wheels, which would have an inner core of the balance wheel made of steel, and then an outer layer around the rim of the balance wheel that was made of brass. And then these would be cut, one on each side, a kitty corner to one another of the arms of the balance wheel. And then you would have screws in the balance as well that could be adjusted in and out. So as the temperature changed, the rate at which the steel expanded or contracted versus the rate at which the brass expanded or contracted differed and caused the arms of the balance wheel to move in or out. And then you could perform very fine temperature adjustments by changing how deeply engaged the screws on the very tips of those arms were. So just like the arms of a figure skater spinning around in circles, you could vary how that balance performed as the temperature changed. And those balances were typically paired with hairsprings that were made of spring steel.
So those were going to be more susceptible to temperature variance than modern ones.
Actually, they're comparable, so you could get a very good rate out of that sort of balance. So the reason that balance was invented was because prior to that, you would have a balance wheel that was monometallic, made of just a single material, and that would change its dimensions as temperature increased or decreased. And you could get errors on the order of minutes a day simply because your balance wheel was a little bit bigger at so many degrees Celsius or Fahrenheit. Now, interestingly, quartz timepieces are susceptible to changes in temperature as well. So if you heat up a quartz crystal, you're going to find that your quartz watch is going to run quite a bit faster left in the, say, the windshield of your car or out on a day at the beach than it will living in, say, the Arctic.
Now, when I take a look at let's say one of my Eterna watch movements that I purchased for my new watches, those balances are single piece and they don't have any of the little oscillating weights that you would see in let's say an old Hamilton pocket watch or something like that. With the older bimetallic wheels, you can use the weights to help adjust for changes and variances, right?
In temperature, yeah.
Right. So with something like this, there's no, there isn't any way of doing that. There are no weights to be able to modify the balance wheel itself. Is the expectation that there's no reason to, or is the expectation that there's some other way of actually moderating or adjusting the timing of it based on temperature changes?
As far as temperature goes, in modern watchmaking, it is a solved problem, in large part due to the breakthroughs brought about by Charles Guillaume and the particular flavor of beryllium copper alloy that is used most commonly in watches today is known as glucider. Interestingly, Nivarox hairsprings or Ellenvar hairsprings are not impervious to magnetic interference. And one of the strange things that can happen when they're magnetized is that they can suddenly become susceptible to changes in temperature. Of course, there are a number of other ways that watches are adversely affected by magnetism, but that is one of the more esoteric ones for sure.
So as a watchmaker, what are you doing to adjust the balance, the rate of the balance, so that it's keeping accurate time? Because presumably that's something that's important to do when you're either building a watch or maintaining a watch, that you need to ensure that rate is accurate. How do you go about ensuring that?
Now, as a watchmaker, I could go down quite the rabbit hole here, but I won't go into things like dynamic poisoning or static poisoning or any of that. For the purposes of our discussion here today, just talking generally, essentially you have 2 points of control. You can change the hairspring and how it's operating and functioning, or you can change the balance wheel and how it's performing. So with the hairspring, what you would be looking at is changing how long it is. Now you can do this very physically by changing where it is actually fixed in place on the balance cock, which is what's holding this entire oscillating unit in place, or you can do it in a more dynamic fashion, and this is the way that the vast majority of mechanical timepieces are regulated today, and this is with a pin regulator. And what you're doing with a pin regulator is you're putting 2 very tiny rods of metal down around the hairspring, flanking it on either side, very close to where it is actually affixed to the balance cock. And without actually touching the hairspring, you can guide and direct these 2 pins backwards and forwards in an arc along the hairspring. And when the hairspring is set in motion, it's going to hit up against those pins, effectively changing the active length of the hairspring. So rather than affecting its force from the point at which is actually physically attached to the balance cock, the force that it is enacting on the balance wheel to restore motion in the opposite direction is going to be occurring where it's smashing in to one of those two pins. So on the outermost pin, what's going to happen is the hairspring is going to be expanding out when it hits that. And when it's expanding out, it's actually going to pull away from the point where it's actually physically affixed, and it's actually going to lengthen very slightly, and you're going to get a slightly slower rate of performance in that direction. And then when it spins back in the other direction, it's going to smash on the pin on the inside. And because this is an arced spring, that arc is going to contract a bit to the point where it's actually fixed on the balance cock, and you're actually going to end up with the active length of the hairspring being shortened, and that's going to produce a faster rate. Because this is happening in a balanced way on every single oscillation of the balance wheel, you can sort of get that to cancel one another out. But what you'll find is most regulators, when they're set up this way, you're going to be angling those two pins that come down around the balance to get as similar a rate out of each of those vibrations as possible. And this is certainly the quickest way to adjust the rate at which the balance wheel is going to be moving back and forth, because you just have to move a little lever that changes where these two pins are positioned. But it is not the most optimal way to change the rate of a watch, because you are susceptible to the errors that are being introduced by the pins, and you are also going to find that the rate is going to vary much more significantly over the course of a day, because the amount of energy that's coming from the mainspring is going to change, which is going to change the amount of energy that's being transferred from the escapement to the balance wheel is going to change, which is going to be the amount of energy that's the balance wheels affecting on that hairspring is going to change. So then those active lengths are going to vary over the course of a day. So you get much less stable timekeeping out of a system like this.
Now, are you going to also run into issues where those pins can move over time? Because while you're talking about the changes in the amount of force that's being applied to them due to the changes in mainspring length, I imagine that unless you fix those pins in place somehow, they are going to be susceptible to some kind of motion over, let's say years between servicing.
I wouldn't say so much that it would happen over time as with impacts or shocks. So you can very quickly change the rate of a pin regulated watch by giving it a hard enough impact. So you'd say drop it on a hardwood floor or bang it into a door jamb. That could be enough to actually shift the position of those pins. And a very small shift is all it takes to have an effect of seconds per day, and then into tens of seconds and all the way up into minutes. So it to me, this isn't my favorite or preferred way for a watch to be regulated. The optimal way, in my opinion, is actually to effect change on the balance wheel itself. So again, going back to that illustration of the figure skater expanding their arms out or in, depending on whether they want to be going faster or slower. What you can do is eliminate those pins. So number one, you eliminate a number of points of error. You can end up with a much simpler system. And this is where we get into the free sprung balance wheels that we sort of kicked this show off on and that we've alluded to in a number of episodes. So a free sprung balance wheel is one where the only point that is defining how long that spring is where it's physically attached to the balance cock. So there are two ways you can create a free sprung balance. There are systems that exist where you can actually change that point of affixation. So you can loosen up some screws and actually move that hairspring in a little bit. And that is a very delicate procedure and not the optimal way, and certainly not a very quick way to go about things. It's quite susceptible to error, both in over adjusting or under adjusting, and also into introducing abnormalities into the spring itself, because you have to clamp the spring down in place. But there are watchmakers who have had success with this particular technique over the years, but the pieces that they are making are certainly not mass produced. For the purposes of mass production, what you want to look at doing is affecting change at the level of the balance wheel. So you will typically have inertia screws or inertia nuts that change the moment of inertia of the balance wheel. And that's just an overly complex way of basically saying the same thing with the figure skater, where you if you turn screws so that weight is moved towards the perimeter of the balance wheel, or even outside beyond the perimeter of the balance wheel. In the case where you're actually using screws, you'll be turning screws out further from the balance. That will cause the balance wheel to slow down. And then if you do the opposite, so turn weight away from the perimeter of the balance wheel towards its center, or move screws in towards the center, then it will speed up. And with a system like this, you are not nearly as susceptible to the fluctuations over the course of a day that you would be susceptible to with a pin regulated balance. And that's why free sprung balance wheels are favored among pretty much any of the great watchmakers, from Breguet and John Arnold down through to George Daniels, Roger Smith, Gary Voutilainen. And then, of course, the watch manufacturers that have earned the most praise and have sort of earned their spots at the top of the heap over the years, Rolex and Patek Philippe. And they both started rolling out free sprung balance systems around the same time, in the middle of last century. And interestingly, both companies rolled out a combination at the outset of a pin regulated spring in conjunction with a balance wheel that has inertia nuts on it. And then over time eliminated the pin regulator altogether and stuck 100% with just the inertia, the screws in the case of Rolex, and inertia nuts or gyromax nuts in the case of Patek Philippe. And they are remarkably stable timekeepers, and really is the best way to go about regulating a mechanical timepiece.
So it sounds like in the case of these free sprung balance wheels, they're not necessarily easier to produce in mass production, but it sounds like they are a simpler system in the long term, particularly when it comes to being able to adjust and regulate them later on.
Mm-hmm. Yeah, there are certainly fewer parts and fewer things that can go wrong with the system. The more parts you add, the more potential points of failure you have, or the more variables you introduce, the more potential bugs you may introduce into a system. So a free sprung balance wheel, it really is a distillation of just that, as getting it as simple as you can. Make something as simple as possible, but no simpler.
Now, with something like let's say these Eterna movements that I've been picking up for my watches, they are currently pin regulated. How difficult is it to take something like that and convert it into a free sprung balance and turn it into this and get the advantages out of it being free sprung instead of pin regulated?
It's entirely feasible. It's kind of a pastime of mine, I guess you could say, converting watches into free sprung systems. There are certainly some challenges. Most of them center around the hairspring and getting the pinning points correct, and getting the length of the hairspring paired well to the mass of the balance wheel. Because when you remove the pin regulating system, you end up with a hairspring that is too long for the balance that it is paired with. So you either need to reduce that length or add weight to the balance. Now, often you'll be adding weight in some form anyway in order to introduce inertia nuts.
I was going to say, looking at the balance wheel on these movements, they are quite small, and there isn't a lot of meat to them. So trying to add those inertia nuts to them would be challenging. So I suspect you would need to increase the mass of the balance wheel anyways, and adding the nuts presumably would add some more mass to it.
Yeah, just potentially remake an entire balance wheel if needed. But to quote Antoine de Saint-Exupéry, who penned Le Petit Prince, the perfection is achieved not when there's nothing left to add, but when there's nothing left to take away. So I would certainly encourage you to try and eliminate that pin regulator if you're game for it. But there's certainly no harm in leaving it in place for your first few rounds of watches.
I expect that the first few I will be leaving very much as is, just because I have other challenges that I need to deal with, such as making cases that I'm happy with and whatnot. And I'm trying to avoid doing too much fiddling with the movement and trying to reduce the amount of work that's involved with the movement side of things. But I can see eventually wanting to do something like this, if only to be able to distinguish the Eterna movements I'm using in my watches from the dozens of other brands that are going to be using the same movements in their watches as well. Certainly anything that I can do to be able to distinguish mine and perhaps make them better timekeepers than others, that would be a huge benefit.
I mean, it's certainly achievable to create a chronometer grade watch with a pin regulated balance. So you just have to go down that other rabbit hole of static and dynamic poising.
Right.
But you absolutely could pull it off. And there's a lot of other variables within the watch that you want to make sure are just right and getting a good, consistent delivery of power from the mainspring through to the balance wheel. But I mean, John Harrison pulled it off when he cracked the longitude problem. I mean, the H4 has a pin regulated balance in it. And, he allowed Britain to conquer the oceans.
Thanks for listening to Off Hours. You can find detailed show notes at offhours.show. If you'd like to keep up to date with the show, follow us on Twitter @offhours. John can be found on Twitter @UnderTheLoop, and Chris can be found on Twitter and Instagram @silver_hand.